Acha, let's read this question. Okay, a cylinder rolls without slipping. That means this is a condition of pure rolling. Pure rolling means V is equals to omega r. Okay, or the velocity out here should be equals to omega into r. Omega into r. Okay, over a horizontal plane, the radius of the cylinder is equals to r. That means this radius is equals to r. Find the curvature of radius of trajectory of path traced out by point A and point B. So what the question is saying is, when this wheel rolls over a surface, okay, this is rolling. Suppose with velocity v, okay, forget this. This is omega angular acceleration. Forget this part. Okay, this point A. What is the trajectory of this point A? The point A will move somewhat like this. Okay, the question is saying find the radius of curvature of the path traced by point A. That means find the radius of curvature of this orbit. Find the radius of curvature of this orbit. Okay. Now, how do I approach this kind of problems? The simple method of approaching this kind of problems is we use centripetal acceleration. Centripetal acceleration is equals to v square by r. Okay, where v is out here is nothing but the total velocity. The v out here is nothing but the total velocity. AC out here is the total acceleration acting normal to the velocity, total velocity. Okay, and r is the radius of curvature. R is the radius of curvature. Okay. Okay. So how do I find out this one? See, whenever there is rolling motion, a rolling motion can be divided into a combination of rotational motion of omega plus a translational motion of v. Okay. Now at point A, due to this translation, is there any acceleration along this component or along this line? No, because this is a constant velocity. Okay. So is there any acceleration along this component or along the vertical because of this velocity? No. Okay. The acceleration because due to this velocity component will always be along this line or along the horizon. So what is the total velocity at point A? The total velocity of point A is v due to translation plus omega r due to rotational, and omega r is fortunately equals to v. Okay, for pure rolling. So the total velocity at top is equals to v plus v, which is equals to 2v, or total velocity is equals to 2v. Okay. Okay. Now what is the total acceleration that is perpendicular to the total velocity? Let's check all the acceleration out here. Is there any acceleration along this component? No. Is there any acceleration along this component? Yes. The acceleration along this component is equals to AC, or AC is equals to how much? V square by small r, or AC is equals to V square by small r, where r is the radius of this wheel. Okay. Now my question is, what is the total acceleration perpendicular to the total velocity? See, the total acceleration perpendicular to the total velocity is fortunately this value, AC. Okay, this is also the total acceleration perpendicular to total velocity at this instant. Total centripetal acceleration, or total acceleration perpendicular to total velocity at point A. Point A. So can I substitute this value out here and this total velocity value out here? So if I substitute this value out here, what do I get? AC is equals to V square by small r, where r, small r is the radius of the wheel. Okay, is equals to V square. What is this V square? This V square is nothing but the total velocity, or 2v whole square by capital R, where capital R is the radius of curvature. So if I cancel this out, v square by r is equals to 4v square by capital R, v square and v square gets cancelled, or radius of curvature is equals to 4 times the radius of the cylinder. This is the first part of the question. Now the second part of the question. What is the total acceleration at point B, or find the radius of curvature of point B. So similarly, if this wheel or if this cylinder was rolling on a road, point B, okay, I have to find the centripetal acceleration of, sorry, I have to find the radius of curvature of point B. So I have to find out this radius, point B. I have to find out this radius. Now, what is the total velocity of point B? See, this rolling motion can be converted into a combination of rotating motion with omega plus a combination of translational motion with velocity v. So at point B, what is the total velocity? At point B, the total velocity at point B is a combination of, see, due to rotating motion, the velocity at point B is equals to omega r, which is equals to v. Okay, so the total velocity at point B is a combination of, total velocity at point B is a combination of vector summation of v due to translational motion plus vector summation of omega r, which is equals to v for rotating motion. So the total summation of these two vectors would be v root 2. How? V square plus v square under root is nothing but v root 2. So this is nothing but the total velocity. Okay. Now I have to find out the acceleration in the component along this line. Okay. Why? Because this line is same as this line. Okay. The angles are a little bit different. This line is same as this line. Okay. And the total acceleration along this line is nothing but the centripetal acceleration or total centripetal acceleration corresponding to this total velocity. Okay, so first we need to find out what is the acceleration present out here. So is there any acceleration present out here? No. Is there any acceleration present out here? No. Is there any acceleration present out here? Yes. The acceleration is centripetal acceleration along this direction. The centripetal acceleration is equals to v square by r, where r is the radius of the cylinder. So see out here, the centripetal acceleration or total centripetal acceleration we have available is along this direction, but we need a component of acceleration that is perpendicular to the total velocity. So can I take the component of acceleration along this line? So first you need to find out what is this angle. Okay, I have to find out what is this angle. This angle, this angle is nothing but 45 degrees. How? See, if this is v, this is v, how much is this angle? This angle is nothing but 45 degree because both the vectors are equal. This line and this line are 90 degree. Why? Because the centripetal acceleration would always be, for radius of curvature, would always be perpendicular to the total velocity. Okay, and this entire line is 180 degree. So 45 plus 90 plus what is 180 degree? Plus 45. So this entire degree makes an 180 degree. So this angle is nothing but 45 degree. So can I say total acceleration along this component is equals to AC cos 45, or is equals to AC cos 45. Now for finding out the radius of curvature, we simply follow centripetal acceleration is equals to v square by r, where centripetal acceleration, total centripetal acceleration perpendicular to the total velocity is AC cos 45. Okay, where v, total velocity, is nothing but v root 2. Okay, and the value of AC, or the magnitude of AC, from this equation comes out to be v square by r. So v square by r. If you substitute everything, v square by r cos 45 1 by root 2 is equals to v root 2 whole square by radius of curvature. Okay, or if I simplify this one, v square by root 2 r is equals to 2v square by capital R. V square and v square gets cancelled, or r radius of curvature is equals to 2 into root 2 r, or 2 into root 2 times radius of the cylinder. Understood this one?
Yeah. To understand this problem, you first need to understand something called gyroscopic acceleration. Okay, gyroscopic acceleration. We'll learn about this gyroscopic acceleration, or let's learn about this gyroscopic acceleration on the next page. So before we start with gyroscopic acceleration, we need to understand something about centripetal acceleration. Okay, centripetal acceleration. Asha, you probably mostly know something about centripetal acceleration, that it is v square by r or omega square r. But thing that I'm going to say out here is a little bit different. Okay, suppose a particle is moving with velocity v. It has a centripetal acceleration that is always normal to the velocity, and centripetal acceleration is given by v square by r or omega square r, where r is the radius of the circular orbit. Fair and fine. The problem with the formula that I have is centripetal acceleration is a vector quantity, and neither of these expression denotes a vector quantity. So how do I denote the direction of a centripetal acceleration? If I do, centripetal acceleration of the vector of centripetal acceleration is nothing but omega cross v. This gives us the direction of centripetal acceleration. The problem is, what is omega? Omega is the angular velocity through which the particle rotates in the circular orbit. Now apply this formula. The direction vector of omega is outside the plane of the screen. This vector is along this direction. So apply your right hand three finger rule, and the direction of centripetal acceleration will be in this direction. That is all fair and fine, but how do I derive this one? See, there are many derivations. Let's check out the derivations that I'm doing. Okay, in this setup, this particle is moving in circular orbit. Okay, this particle is moving in circular orbit with velocity v. The centripetal acceleration will act in this direction. So the thing that I'm going to use to derive centripetal acceleration is the standard one, where acceleration is equals to dv by dt, or acceleration is equals to rate of change of velocity. The problem I have out here is that velocity out here is a vector quantity, but that vector changes with respect to time. So how do I define this vector in a circular orbit? Okay, so suppose there is a circular orbit out here. Okay, and this particle was initially out here with velocity v. Now how do I define the velocity vector v? So for that instant, what do I do? This particle is rotating with angular velocity omega. See, the particle is rotating with angular velocity omega. Is the omega constant? It might or might not be. If the angular velocity is constant, the magnitude of centripetal acceleration will always be constant. If the value of omega is not constant, or the value of v is not constant, what will happen? The value of centripetal acceleration will, or the magnitude of value of centripetal acceleration will vary from time to time. That's fair and fine. So for now, just for the interest of centripetal acceleration, what we'll do, we'll assume the velocity to be constant, so the omega will be constant. So what will happen after certain time? So say after time t, okay, the particle reached out here. Now it is moving with velocity v, that is normal to this. Okay, how much is this angle? This angle is nothing but omega into t. How? I can easily use the relation theta is equals to omega t plus half alpha t square. And since for the scope of centripetal acceleration, I have assumed the omega to be constant, so there is no acceleration. So if I take acceleration to be 0, so theta is equals to omega t. So at time t, that distance or the radiance this axis traveled is equals to omega t. So this degree is nothing but omega t. So my main question is, how do I write this vector v, okay, as a function of time? Okay, see, can I shift this vector out here, v out here? Of course I can. So if I shift this vector v out here parallelly, what do I get? I get this line, okay, and if I draw a simple straight line from the radius, I get this line. How much is this much angle? This much angle is nothing but 90 degrees, is same as this much angle because I shifted this line parallel out here. So this much is 90 degree, and this entire line makes a 180 degree. So if this is omega t, this is 90, this should be 90 minus omega t. So I'm writing 90 minus omega t as omega t dash. Okay, and this is velocity vector. Now I can write velocity vector as a function of I and j. Okay, it is nothing but v cos omega t dash, cos omega t dash, or cos 90 minus omega t. Cos 90 minus omega t is nothing but v sine omega t I. Actually, it is minus of v sine omega t I. Why? See, if I denote this direction as x and this direction as y, positive y axis, this direction as z axis, this direction will be positive x axis, but the velocity vector is opposite to the direction of positive x axis. This component of velocity is opposite to the direction of positive x axis, so it will be minus of v sine omega t I plus v cos omega t j. Is there any k component of this velocity, or is there any z component of this velocity? No. Okay, because the entire thing happens in xy plane. Okay, now let's check out here. What's the value of omega t? 0. So when this entire value is 0, the velocity of, or the entire velocity becomes v cos omega t or vj, which is correct according to the notation. The velocity is towards positive x-axis. Out here, what's the value of omega t? The value of omega t is 90. So if you put 90 in this equation, this becomes 1, this becomes 0. So the value of velocity would be minus v towards negative x-axis. So out here velocity is towards this direction. Out here the value of omega t is equals to 180. So you get the gist. What I have done expressively out here is I have expressed the term v in terms of I and j with the help of time. Okay. Now I can simply use this relation to find a. A is equals to dv by dt. Now what this acceleration will give us is the centripetal acceleration. Why? Because the magnitude of velocity does not change, only the direction changes, and that direction is given with respect to time by this notation. So if I differentiate this notation with respect to time, I'll simply get the acceleration, and that acceleration is called the centripetal acceleration. Okay, so let's differentiate this term. Let's differentiate this term with respect to t. What do I get? I get minus v omega, or minus omega v cos omega ti minus omega v sine omega t j. Okay, one more doubt we might have is, how is omega into v equals to v square by r? You can simply write omega is equals to v by r, no? Okay, so this expression and this expression are nothing but same. Okay, this is just the proper vector notation of these expressions. Okay, you can simply write v as omega square r, and you can simply get centripetal acceleration is equals to omega square r. So these magnitudes and these magnitudes are essentially the same. Okay, do not get confused out. So let me get back to my derivation. Acceleration is given by minus omega b cos omega ti minus omega v sin omega tj. Now let's check if these are uh, okay or not. Out here, what's the direction of acceleration? Towards negative x-axis. So put omega t is equals to 0. So this entire time becomes 1 and this entire term becomes 0. So at omega t is equals to 0, acceleration is towards negative x-axis, and the value is omega into v, which is essentially v square by r or omega square r. Okay, v can be written as omega r. Okay, you substitute any one of the following into other, we'll get the either of these two values. You get either of these two values. So what I'm trying to say is this is the proper vector notation of centripetal acceleration. See, even if you find the magnitude of centripetal acceleration, what happens? How do I find out the magnitude? It's x square plus y square. Okay, because x component of acceleration is this one and y component of acceleration is this one. So minus omega b cos omega t whole square plus minus omega b sin omega t whole square. Okay, if you take omega b constant or omega b common, omega b square under root of cos square omega t plus sin square omega t. Okay, this will become as 1 because cos square theta plus sin square theta is equals to 1. Okay, so this will essentially come as centripetal acceleration is equals to omega v, which is essentially this formula. Okay, which is equals to v square by r, which is equals to omega square r. Now, why did I write gyroscope? Why did I make you understand centripetal acceleration in topic of gyroscopic acceleration? We'll use similar approach to derive gyroscopic acceleration. Okay, where acceleration is equals to dv by dt. Now let us take a case of wheel rotating. Okay, let me draw the axis. This is x-axis. This is y-axis. This is z-axis. Okay, suppose there is a wheel in x-axis. The wheel is rotating with angular velocity omega. Okay, the wheel is in yz plane. Okay, what is the axial vector of this angular velocity? The axial vector of this angular velocity, if you use right hand rule, is omega. Okay, fair and fine. Now, along with this rotation, the wheel is also revolving around a circular orbit in xz plane. So the wheel is also revolving around this circular orbit. Okay, if we see this motion from top, how would I see it? Let me draw the axis. I'm seeing this entire motion from the top. Okay, so from the top, the axis will appear as this as the x-axis, this as the z-axis, and the wheel is out here rotating with angular velocity omega. And this wheel is also revolving in circular orbit in xz plane. Okay. Now, after a certain while, what will happen? When the disk reaches out here, what will be the angular velocity vector? Along this direction. When the disk reaches out here, what will be the direction of angular velocity? Along this direction. When the disk reaches out here, what will be the direction of angular velocity? Along this direction. So you can see as the disk is rotating, okay, the direction of the angular velocity is changing, although the magnitude of angular velocity remains constant. So to change the direction of angular velocity, there must be some acceleration present, and that acceleration is called gyroscopic acceleration. To understand it, similar to centripetal acceleration, see, in a circular orbit, okay, for centripetal acceleration, what happens? The velocity remains constant, the magnitude of velocity remains constant. Okay, the magnitude of velocity remains constant. Only the direction of velocity changes, and that change in direction is caused by the centripetal acceleration. That means centripetal acceleration is causing the velocity vector to change the direction of its vector. Similarly, the acceleration that is helping this omega to change its direction is called the gyroscopic acceleration. Okay, so the gyroscopic acceleration would be out here. The gyroscopic acceleration would be out here the gyroscopic acceleration would be out here, the gyroscopic acceleration would be out here. Asha, how do I know? There is a formula for finding out gyroscopic acceleration, but let us understand the similarity between centrifugal acceleration and gyroscopic acceleration. Okay, see one more thing. Acceleration vector will always try to change the velocity vector towards itself. See, acceleration vector is towards this direction. So after a certain while, the velocity vector becomes in this direction. Out here, acceleration vector is in this direction. So after a certain while, velocity vector becomes in this direction. So acceleration vector is in this direction. So after a certain while, velocity vector becomes in this direction. Similar kind of things occurs out here. Okay, velocity vector is in this direction, or angular velocity vector is in this direction. Acceleration vector is in this direction. So after a certain while, angular velocity vector becomes in this direction. Out here, the acceleration is this direction. So after a certain while, the angular velocity becomes in this direction. Out here, the acceleration is in this direction. So out here, the angular velocity becomes in this direction, and so forth. So if I say centripetal acceleration vector is given by omega cross v, out here gyroscopic acceleration or gyroscopic angular acceleration is given by omega p cross omega. Now what is this omega p? Omega p is nothing but the angular velocity with which the disk revolve around this circular orbit, or the velocity of revolving around the circular orbit is called angle or angular velocity or angular velocity of precision. But omega is the angular velocity of the wheel. That means omega is the velocity through which the wheel rotates. Omega p or precision angular velocity is through which the wheel moves around this circular orbit. That much is understood. But how do I derive this? We derive this using the same principle, where acceleration is equals to rate of change of angular velocity. Okay, similar to the derivation of centripetal acceleration. Okay. Now for centripetal acceleration, we use dv by dt. Out here for angular acceleration, we'll use d omega by dt. Out here, we have the same problem. Okay, the omega is changing, the omega vector is changing throughout. Okay, so we have to express omega in terms of I and j and k. So omega vector is equals to how much? Suppose after a certain while, okay, if I draw the same diagram out here, okay, let me draw the same diagram out here. I drew this same diagram out here. Okay, initially the disk was out here. After time t, the disk reached out here. So after time t, the disk reached out here. So how much is this much angle? This much angle is nothing but omega p into t, or omega p into t. See, initially the disk was out here. Initially the disk was out here. Out here. After time t, the disk reached out here, or disk reached somewhere out here, or the disk reached somewhere out here. So this much angle is nothing but angular velocity into time. Okay, so how do I describe this vector in terms of I, j and k? This omega vector in terms of I, j and k. Always remember, this out here is the x-axis, and when I'm looking from the top, this out here is the z-axis. So if I express omega in terms of I, j and k, it will be omega cos omega pt I, k, minus omega sin omega pt k. Why? Because if downward is positive z direction, upward or omega sin omega pt would be minus of k. Okay, so this is minus k. This is the value of omega as the time passes. See, let's check. At omega pt is equals to 0. Okay, the direction of angular velocity is towards x direction. Put the formula of omega pt is 0. We get the value of omega to be at I. Out here, omega pt is equals to 90. Put it, we get the same value. Out here omega pt is equals to 180, we'll get the same value. Out here omega pt is equals to 270, we'll get the same value towards z direction. So you get the gist what I did outside. I did with the same thing I did with the velocity. And now for deriving acceleration, acceleration is equals to rate of change of angular velocity. Okay, and this acceleration out here, okay, this acceleration out here is nothing but the gyroscopic acceleration. Why? Because I'm finding out the acceleration that is causing the change in direction of this angular velocity vector. Okay, so d omega by dt, when you differentiate this entire term, okay, with respect to time, what do I get? I get omega p omega minus of sine omega pti, okay, minus omega p omega cos omega pt k. Okay, let's put the values out here. At omega pt is equals to 0, this entire term becomes 0. The value of gyroscopic acceleration is towards positive k axis, sorry, towards negative k axis. So at omega pt is equals to 0, the direction of and gyroscopic acceleration would be towards this one. At omega t is equals to 90, the direction of gyroscopic acceleration would be towards this side. Okay, so you get the gist. What is the magnitude of gyroscopic acceleration? Ag. The magnitude of gyroscopic acceleration is nothing but x square plus y square plus z square under root. So sine omega pt whole square plus minus omega p cos omega pt whole square under root. Okay, now if you take omega p and omega common, we'll get angular acceleration. Okay, magnitude of angular acceleration is equals to omega p into omega. Okay, the vector form of the same formula is angular acceleration vector is equals to omega p cross omega. This is the entire thing I want you to prove, or I want you to understand about gyroscopic acceleration. That there is a acceleration which causes a change in direction of velocity vector, and that acceleration is given by omega p cross omega. Similarly, there is a acceleration that causes a change in direction of velocity vector, but that acceleration is given by omega cross v, or v square by r, or omega square r. Similarly, there is a acceleration that causes the change in direction of angular velocity vector, and that acceleration is known as gyroscopic acceleration. Okay, now one more important thing I missed out here. Suppose someone says, okay, this wheel was rotating along this direction, or the angular velocity vector along this one. This wheel was also rotating along this orbit, or revolving around this orbit with angular velocity omega p. My next question is, write down the total velocity that this will have. Write down the total angular velocity that this will have. What you do? Okay, just think for a minute. And to write down the total angular velocity of this wheel. Okay, total angular velocity of the wheel. Of the wheel. See, this wheel has two angular velocity. One is omega and the other is omega p. What is the direction of omega p vector? If the wheel is rotating along this axis, we use right hand rule, the direction vector of omega p would be along this direction. Okay, so the total acceleration, sorry, the total velocity of the wheel, or the total angular velocity of the wheel would be how much? Would be omega vector plus omega p vector. Okay, where omega vector is along this axis, omega p vector is along this axis. The combined angular acceleration will be around this axis, or this would be the combined acceleration vector, sorry, angular velocity vector, which would keep rotating as the wheel moves in this circular orbit. Okay, and that is caused by gyroscopic acceleration. So how do I take total angular velocity? Total angular velocity is equals to, how do I express omega in terms of t? Omega, this was omega pt. So omega cos omega pt I minus omega sin omega pt k, and there was another term omega p j plus omega p j. Okay, now what happens if the revolution, or if omega p changes with respect to time? If omega p changes with respect to time, the magnitude of gyroscopic acceleration will change with respect to time. Similarly, if velocity changes with respect to time, the centripetal acceleration will change with respect to time. Okay, so similar things happens when we change the, or if there is an acceleration in this orbit. Okay, the value of gyroscopic acceleration will change from time to time. Okay, so to find out the instantaneous gyroscopic acceleration in that case. Okay, so the total angular velocity when a wheel rotates around one axis and that axis also revolves around a circular orbit, then the total angular velocity is given by the angular velocity of the wheel expressed in time plus the angular velocity of the axis. This is the concept I need to understand. Okay. Now let's read the question. Two solid bodies rotate about a stationary mutually perpendicular intersecting axis with constant angular velocity omega 1 and omega 2. Okay, with 3 radians per second and 4 radians per second. Find the angular velocity and angular acceleration of one body relative to another. So what the question is saying is there are two perpendicular axes. Okay, and there are two disks. Let's assign the disk as the to avoid confusion. Disk 1 and disk 2. Disk 1 is rotating with angular velocity omega 1, which is equals to 3 radians per second, and disk 2 is rotating with angular velocity omega 2 with 4 radians per second. Okay, radians per second. This disk rotating this direction, this rotating this direction. I'm just expressing the angular velocity vectors. Okay, by using right hand rule. Okay, find the angular velocity relative to one another. So if you need to find the angular velocity relative, what do? You put our observer in one frame. So when you put our observer in one frame, what happens to the body 1? Suppose we put our observer in 2. Okay, our observer is in body 2. What happens? Body 1, this is body 1, this is body 2. Body 1 already has an angular velocity of omega 1 in this direction, and whenever we put our observer in any frame, what do? We just take the velocity of the frame and apply it to all the bodies in opposite direction. So out here the velocity of the frame is in upward direction, or what I'll do is I'll apply the velocity in downward direction. So the combined angular velocity or the relative angular velocity would be in this direction, or omega 1 plus omega 2. Okay, which would be, or omega 1 2 relative, or relative velocity of 1 with respect to t is nothing but omega 1 plus omega 2. What is the magnitude? The magnitude of that relative velocity is nothing but omega 1 square plus omega 2 square. Okay, this is a simplified form of understanding the question. Okay, but what do I do if I want to understand the whole setup? See, if I look at the top view, suppose this is x-axis, this is y-axis. I'm looking from the top. Okay, when I'm looking from the top, this is z-axis. So if I'm looking from the top, this will be x-axis, this is y-axis, sorry, this is z-axis, and the y-axis will be coming towards you. This is wheel 1, okay, and this is wheel 2. Wheel 2. Okay. The wheel 2 is rotating in this direction with omega 2 velocity. Okay. Okay. If you put your observer out here, okay, imagine yourself to be sitting on the rim of this disk. What will happen? You will see this disk moving in this direction, rotating in this circular orbit. No, you'll see this disk rotating in this circular orbit. Okay. So what happens is this disk starts moving in this direction. Okay, with the angular velocity of omega 2. When you are observing from this frame, okay, what will happen is this axis will try to rotate with angular velocity omega 2 in this direction. Is that understood? Okay, just imagine yourself sitting at the rim of the disk. If you are rotating, the world revolves around you, no? The world rotates around you. Similar thing is happening out here. Okay, this axis revolves with the angular velocity of this disk in opposite direction. And this disk or omega, this one already revolves with angular velocity omega 1. Okay, so how do I write omega 1 2 or relative velocity of 1 with respect to 2 in terms of vector quantity? See, in terms of vector quantity, this vector would keep on changing its direction, or this vector would keep on changing its direction. What will happen is this vector would rotate in this circular orbit. This vector would rotate in this circular orbit. Why? Because the direction of omega 1 will keep on changing in this circular orbit according to the observer. Okay, direction of omega 1 would keep on changing radially outward in this circular orbit. Understood? So after a certain while, the direction of omega 1 will be in this direction, and the magnitude of resultant velocity would be inward, which is equals to omega 1 square plus omega 2 square. Out here, the direction of omega 1 and the magnitude of total angular velocity would be this vector plus a vector that is inward, which is equals to this direction, a slanting vector towards the inside of the plane. Okay, so how do I express relative velocity or angular velocity of 1 with respect to 2 in vector form in ij and k? Okay, so say suppose after certain time the disk has rotated out here. Okay, angular velocity omega 1. What is this much angle? This much angle is nothing but omega 1 into t. Why? Because omega 1 is constant out here. Okay, so can I write omega 1 2 as relative velocity of 1 with respect to 2 as omega 1 cos omega 1 t, sorry, omega 1 cos omega 2 t. Why? Because this 2 or this axis will be rotating with the angular velocity of the disk 2. Okay, if you are rotating in a disk, you'll see the world revolving around you with the disk you are sitting in. Okay, so this is nothing but omega 2 or the angular velocity of this disk. Okay, so omega 1 or omega 1 cos omega 2 t, cos omega 2 t. What is this direction? I cap plus omega 1 sin omega 2 t k cap. Okay, plus omega 2 1 sin omega 2 k cap or along positive direction. Acha. Is this the total angular velocity this will have? This will also have an angular velocity of omega 2 along this direction. No, the axis is also moving along this direction. So we have to write plus omega 2. And what is the direction of omega 2? If the omega 2 is along this direction, okay, the omega 2 will be inwards. What is inwards?
towards negative y-axis. Okay, omega 2 minus j cap minus j cap. But if you take this minus outside, it will be minus omega 2 j cap. Okay, j cap. And when you find out the magnitude of omega 1 2, okay, you just take this square plus this square plus this square under root. Okay, and so omega 1 cos, let me just write this down. Okay, and when you solve this expression, you get the magnitude of relative velocity of this one with respect to this two as omega 1 square plus omega 2 square, which is same as the velocity obtained by previous method. Okay, now let's solve for part 2 of the question. Find the relative angular acceleration with one body relative to another. Does this acceleration seem similar to gyroscopic acceleration? Yes. So what's the acceleration? Acceleration is nothing but omega 2 cross omega 1. Okay, where this acceleration is trying to change the direction of velocity vector towards itself. Okay, so acceleration, angular acceleration would be omega 2 into omega 1. But suppose I want to use the differentiation method, or I want to use this method for angular acceleration is equals to rate of change of angular velocity with respect to time. So I can simply write the total velocity and differentiate it. The velocity was given by the term velocity total is equals to, this was the total velocity we had. Okay, okay, and since the, this one is j, and since this omega p or precision angular velocity remains constant, therefore the magnitude of gyroscopic acceleration will always remain constant. So out here angular acceleration is equals to d omega by dt. Okay, when you differentiate this, what do we get? Omega 1 or omega 2 omega 1 minus of sine omega t. Okay, plus this omega p is constant out here. So what happens when you differentiate a constant with respect to time? It becomes 0. So plus 0 j. Okay, if this omega p was not constant, what would happen? The magnitude of gyroscopic acceleration would change with respect to time. So it would have an instantaneous gyroscopic acceleration. Okay, and the total acceleration which would be obtained by differentiation of this formula would be something else. Okay, or if we find out the magnitude of gyroscopic acceleration, you simply do a square plus b square plus c square under root, which would give us the value of omega 2 into omega 1. Now let us read this question. A solid body rotates with an angular velocity of omega is equals to at plus btj. So omega vector is given as ati plus bt square j. Okay, where the value of a and b is given, I and j are unit vector along x and y axis. Find the modulus of angular velocity and angular acceleration. So to find out the modulus of angular velocity, it is nothing but x square plus y square under root of at x component whole square plus bt whole square. Okay, at t is equals to 10. So if you substitute the values of a is equals to 0.5, b is equals to 0.060, t is equals to 10, t is equals to 10 out here, we'll get the value of 7.81 radians per second. Now the second part of the question is find the angular acceleration. So omega is given, angular acceleration vector is equals to d omega by dt. Okay, or is equals to a I. If we differentiate this term with respect to t, what do I get? A plus 2 bt j. Okay, and I have to find out the magnitude of this angular acceleration vector. The magnitude of angular acceleration vector is nothing but under root of a square plus 2bt whole square. If I put the values out here, angular acceleration is equals to 1.3 radians per second square. Up till here was plain and simple. Now the second part of the question is find the angle between vectors of angular velocity vector and the angular acceleration vector at that moment. So whenever you have to find the angle between two vectors, always use dot product. What is dot product? A dot B is equals to magnitude of A into magnitude of B into cos theta. So if I find A dot B or A dot B divided by A into B is equals to cos theta. So if I find this value, if I find all these value, or if I find the value of cos theta, I can easily get the value of theta. So let's find out the first part, A dot B. Okay, so A dot B at the moment t is equals to 10. At the moment t is equals to 10. So A dot B is nothing but dot product of, acha. So out here, I have to find the angle between velocity vector and angular acceleration vector, angular velocity vector and angular acceleration vector. So similarly, I can use omega dot alpha by magnitude of omega into magnitude of alpha is equals to cos theta. Okay, so out here, what is omega dot alpha? Okay, omega dot alpha. Omega dot alpha is nothing but omega ATI plus BT square J dot alpha is nothing but how much? AI plus 2BT J. You multiply I with I and J with J. AT into A is nothing but A square T or A square T, and I into I is nothing but 1. So this is scalar addition plus BT square into 2BT is nothing but 2B square T cube. 2B square T cube. Okay. If I solve this entire value, or if I substitute the value at t is equals to 10, I get this is equals to how much? 9.7. 9.7. So we know that dot product of alpha, omega and alpha at t is equals to 10 is equals to 9.7. Okay. Now the second part of the question. What is magnitude of omega into alpha? So magnitude of omega and alpha at t is equals to 10 is nothing but 7.81, sorry, 7.81 into 1.3. So 7.81 into 1.3, which is equals to 10.15. So the value of cos theta out here, cos theta is equals to A dot B or omega cross alpha, which is equals to 9.7. Omega cross alpha is equals to 9.7. Okay, divided by magnitude of omega into magnitude of alpha, which is equals to 10.153 divided by 10.153. Okay, or cos theta is equals to 0.955. Now if we use the inverse function, if cos theta is equals to 0.955, theta is approximately equals to 17. Now let's read the question. A round cone with half angle alpha is equal to 30 degree. That means half of this angle is equals to 30 degree. The entire angle is equals to 60 degree, or 2 alpha is equals to 60 degree, or this entire angle is equals to 60 degree. Okay. Of radius r is equals to 5. So that means this radius was equals to 5 centimeter. Okay. Rolls uniformly without slipping over a horizontal plane, as shown in figure 1.8. That means this cone rotates or rolls in this circular path uniformly with velocity 10 centimeter per second. Okay. So the velocity of point C, that means the tangential velocity of point C, is equals to 10 centimeter per second. Okay. Now before doing anything else, let's draw the axis. This axis is nothing but x-axis. This axis is nothing but y-axis. And this axis is nothing but z-axis. Okay. So this is x, this is y, this is z. Okay. Let me erase the axes from here. Okay. Okay. Find the modulus. Okay. Find the modulus, the vector of angular velocity of the cone and the angle it forms with the vertical. Okay. So if I see the top view means I'm looking from top of y-axis. Okay. What would I see? I would see x-axis and z-axis. Okay. And a wheel that is rotating in a circular orbit around this circular orbit. Okay. The velocity of the center point is v. Okay. And this is a case of pure rolling, rolls uniformly without slipping. That means v is equals to omega r. In case of pure rolling, v is equals to omega r. So the angular velocity of this wheel, the angular velocity of this wheel, okay, or the angular velocity of this wheel would be equals to omega r. Okay, is given by v is equals to omega r. So we can easily say v is equals to omega into r, or omega is equals to v by r. Okay, this much is done. So this wheel by rolling is also moving in this circular orbit. So after a certain while, the wheel will be out here with angular velocity out here. The wheel will be out here with angular velocity out here. The wheel will be out here with angular velocity out here. So this axis is also revolving in this circular orbit. What is the angular velocity of precision? Okay, what is the angular velocity P? See, it is given in the question. V is equals to 10 and this velocity is constant. So if we find the perimeter of the entire circular orbit, can I find out the angular velocity P? Angular velocity P is given by the relation V is equals to omega P into this length, where this length is nothing but the length of the cone. Okay, length of the cone. And how do I find out the length of the cone? Now what I'm trying to do is I'm trying to see the same diagram from Z axis. Okay, from Z axis. That means I'm drawing XY plane. So if I draw XY plane, X plane, Y plane, how would the cone look like? The cone would look like somewhat like this. Okay, with angular velocity omega in this direction. The radius of the cone is 5 centimeter. That means this is 5 centimeter and the half angle is given by 30 degrees. So can I find out this length? Let's say this length as base. Okay, I know that perpendicular by base is nothing but tan. So tan 30 is nothing but perpendicular by base. Where perpendicular is 5 centimeter, base is the variable b. What is the value of tan 30? Tan 30 is nothing but 1 by root 3, or 1 by root 3 is nothing but 5 by b, or b is equals to 5
root 3, or this entire length is nothing but 5 into root 3. So this much I got by basic trigonometry. 5 into root 3 is this much length, 5 into root 3 centimeter. So this much length is nothing but 5 into root 3, okay, centimeter. So let's name this L, or let's use the variable L. We'll substitute all the variables at the end. Okay, so can I say V, or velocity with which this disk moves, or velocity with this disk moves, V, okay, is equals to omega p into L. Okay, why? Because the entire perimeter of the circular path is how much? Perimeter, or perimeter is equals to how much? Perimeter is equals to 2 pi L. You don't need the perimeter. The main point out here was V is equals to omega into R, omega into R, omega into R. Why? Because of pure rolling. And V is equals to omega p into L. Why? Because in circular orbit. Okay, so out here I'll get precision angular velocity is equals to V by L. Okay, now how do I express omega in terms of t time? Omega in terms of time is written as, or one more thing, what is the total angular velocity? Total angular velocity is nothing but angular velocity of the wheel plus angular velocity of the orbit. Okay, how is angular velocity of the wheel written in terms of time? See, if it is rotating with angular velocity omega p, after certain time it will reach out here. Okay, this angle is given by omega p t. So the angular velocity omega will be written as omega into cos omega pt I, okay, minus omega sin omega pt j, not j, k. Why? Because this is negative z direction. See, sine of this omega would be in negative z direction. If this is positive z direction, this would be negative z direction. That's why this minus. Okay, plus what is the angular velocity? If the wheel is rotating in this direction, okay, if the orbital velocity is in this direction, the velocity would be towards the, or out, means towards yourself, or outside the screen. Outside the screen is nothing but towards positive y-axis, or towards positive y-axis. If the wheel is rotating in this orbit, okay, this wise, the omega p would be along positive y direction, or this is the direction of omega p, or precision velocity, or plus omega p j. Okay, now the question is the velocity vector of angular velocity. This is the velocity vector of angular velocity, okay, of the cone, and the angle it forms with the vertical. Acha, what does this vector form with the vertical? Okay, the vector it forms with the vertical is this vector, okay, and this vector will form somewhat this vector, okay, will keep revolving around this axis. See, this omega, okay, will change with respect to time, no? So although the resultant vector is in this direction, this vector would rotate in this circular orbit with respect to time. Okay, similar to what happens with centripetal acceleration. Although the centripetal acceleration is in this direction, but the direction of centripetal acceleration changes with respect to time, no? Similarly, although the resultant velocity vector will be in this direction, okay, let's see, yeah, in this direction, omega plus omega p square, this velocity vector would keep rotating in this direction with the same magnitude. That means this vector would keep rotating along this circle. Okay, okay. And what's the direction? Direction is nothing but, let me draw the diagram more neatly. Okay, let me erase this one. Let me erase the cone. The resultant velocity of omega p and omega would be along this direction. It would be along this direction. Omega plus omega p. But this vector would keep rotating around this circular orbit. No? Why? Because the direction of omega keeps on changing. So after a certain while, the value of direction vector of omega plus omega p would be in this direction. After a certain while, it would be in this direction. So this vector would keep revolving around this circular orbit. But the magnitude of this vector would always remain same, no? And the angle it makes with this vertical, the angle this resultant vector makes with the vertical will always remain same. So suppose this angle is theta out here. This angle will be theta out here. Okay. So can I say tan theta is equals to perpendicular by base, or omega p by omega p by omega. And what is the magnitude of omega? Omega v by r. Okay, the magnitude of omega is v by r. So tan theta is equals to, this would be replaced by v by r. What is the magnitude of omega p? Is v by l. So omega p is nothing but v by l. Okay, we're dealing with only the magnitudes. Okay, so v by l divided by v by r, or tan theta would be how much? V and v would get cancelled, so it would be r by l. Now put in the values of r and l and find the value of tan inverse of theta. Understood? Now the second part of the question, the vector of angular acceleration of the cone. So simply if we differentiate this total angular velocity with respect to time, we get the angular acceleration of the cone. So it is nothing but omega p omega minus of sine omega pt I minus omega p omega cos omega pt k plus, acha, is this omega p constant? Of course, because the velocity is constant, the omega p will be constant, plus 0k, plus 0k, or acceleration would be equals to minus omega p, this value. Okay, if I want to find out the magnitude is nothing but omega p into omega, is same as the gyroscopic acceleration. What is happening out here is acceleration would be in this direction at the starting, outer acceleration would be in this direction of the outer acceleration would be in this direction, outer acceleration would be in this direction, and the magnitude of this gyroscopic acceleration is same, although the acceleration itself is perpendicular to the angular velocity of the cone and precession velocity of the revolution of the axis. Understood? Now let's read this question. Okay, a solid body rotates with a constant angular velocity of 0.5 radian seconds about a horizontal axis AB. So there is a horizontal axis AB, and this body rotates with a constant angular velocity of omega naught. Okay, the omega naught velocity being in this direction. Okay, now at the moment t is equals to 0, the axis AB starts turning about a vertical with a constant angular acceleration of v naught is equals to 10 radians per second. That means suppose this is x-axis. Okay, if this is y-axis and if this is z-axis. Okay, this axis or axis AB starts revolving around this plane with angular acceleration. Okay, what is the angular acceleration of this rotation? Angular acceleration is equals to 0.1 radians per second. Let the beta not be alpha. Okay, for the ease of calculation. See, if I look from the top, okay, this is x-axis, this is z-axis, this is the wheel, this is the angular velocity of the wheel, and the wheel starts rotating with in a circular orbit. Achha. Let's make this a little bit down. The wheel starts revolving around this circular orbit. Okay, but instead of making or revolving around with constant angular velocity, it revolves around with constant angular acceleration. Okay, so by the same method, after certain time t, okay, after time t, how much would be this angle? This angle is nothing but theta is equals to omega t plus half alpha t square. Okay, okay. If the acceleration was not constant, you use d theta by dt is equals to whatever, sorry, d omega by dt is equals to whatever the acceleration was given. So this angle is equals to given by this expression. Whereas initial angular velocity, see, at moment t is equals to 0, the axis starts turning about the vertical axis. Starts turning about the vertical axis means this omega is equals to 0, or this omega is equals to 0. Or the angular velocity, initial angular velocity about the rotation of the axis is equals to 0. So this angle would be nothing but half alpha t square. So this is nothing but half alpha t square. And the angular velocity is already in this direction. Okay. So find the angular velocity and angular acceleration. So what is the angular velocity? Total angular velocity is nothing but omega naught vector plus this vector, omega naught vector plus this vector, or omega naught vector, or angle of, or angular velocity of the wheel plus precision velocity of the wheel, or velocity of the axis. Okay, now this is constant. Okay, the value of this is constant. Omega naught is always equals to 0.5, and this is already changing its direction. Okay, this value of omega p will depend on omega p is equals to omega initial t, or omega initial plus alpha t. Okay, this is omega initial t plus half a t square, where omega initial was equals to 0. So omega p at 3.5 second, is equals to alpha, which is equals to 0.1 into t. So this is nothing but alpha into t. Okay, so out here, find the angular velocity and angular acceleration. See, angular velocity could always be, see, this omega naught and omega p. Omega p is always in y-axis. This is the direction of omega p. So although the direction of omega naught is changing along this circular orbit, this omega naught and omega p will always be perpendicular to each other. Okay, so omega total is nothing but, or total magnitude of total angular velocity is nothing but omega naught square plus omega p square. Okay, I needed to find out the value, which is equals to 0.5 square plus, what is alpha t? Alpha is nothing but 0.1 into 3.5. Okay, which is equals to 0.35 radians per second square. So 0.5 square plus 0.35 whole square under root. If I solve this one, it would be equals to approximately equals to 0.6 radians per second. Okay, now the next part of the problem. Now the next part of the problem, the angular acceleration. See out here. Angular acceleration is nothing but the acceleration of precision velocity plus the gyroscopic acceleration. What is gyroscopic acceleration? The acceleration due to which this omega naught changes the direction of the how much? Changes the direction of the this omega naught. See, this omega naught changes the direction at various part of the circle, no? So the acceleration for which is responsible for the change in direction is called gyroscopic acceleration. So gyroscopic plus rate of change of dt. Okay, and this acceleration is already given by how much? 0.10 radians per second. 0.1 radians per second. Okay, now you have to find out the gyroscopic acceleration. Gyroscopic acceleration is nothing but omega p cross omega. Okay, and see this omega p, the magnitude of omega p changes with respect to time. So what will happen? The gyroscopic acceleration will change with respect to time. Fortunately for us, we have to find the angular acceleration, total angular acceleration at t is equals to 3.5 seconds. So at t is equals to 3.5 seconds, what is the gyroscopic acceleration? We simply have to find the precision angular velocity at t is equals to 0.5 second, which is equals to 0.35. Okay, where omega is equals to how much? Omega is equals to 0.5 and this is equals to 0.1 radians per second. Now you have to find out the angle between gyroscopic acceleration and the rate of change of precision acceleration. See, gyroscopic acceleration will always be perpendicular to both the angular velocity of the wheel and precision angular velocity. Okay, this will always be the direction of gyroscopic acceleration. See, and one more thing, gyroscopic acceleration. See, one more thing, gyroscopic acceleration is in this direction. So gyroscopic acceleration would be in outer negative z direction, outer negative x direction, outer along positive z direction, and outer along positive x direction. So one thing you notice out here is that the gyroscopic acceleration is always perpendicular to the acceleration of rate of change of this precision velocity. The rate of change of precision velocity or this value or alpha p, okay, rate of change of precision velocity will always be along this direction. Okay, why? Because this omega p is increasing with respect to time and it is increasing with respect to time in this direction. So angular acceleration will be along the direction of omega p. Okay, so this angular acceleration and this gyroscopic acceleration will always be perpendicular to each other. The angular acceleration would be out of the plane, the angular acceleration would be out of the plane, and gyroscopic acceleration would always be perpendicular to both omega p and omega. So angular acceleration out here is equals to 0.35 into 0.5 whole square plus 0.1 whole square under root. Okay, it is similar to centripetal force. Okay, if the velocity is changing with respect to time, what happens? There are two components of force, one is the tangential component and another is the centripetal component. Okay, similarly out here, if this is accelerating with respect to time, there are two components of angular acceleration. One is along the along the rate of change of angular acceleration and another is the actual centripetal, sorry, not centripetal, gyroscopic acceleration. Okay, if you put out the values, it would be equals to 0.2 radians per second square.